session 3, which is all about advancements and initiatives in sustainability resources. We'll have talks from Célia, Zoe, Mel, Eva, Clotilde, and Orlando. They'll all be having 7 minutes for their presentations. They will all be presenting their own slides, and I will be very hot on the timer button as well. So apologies if I interrupt you, but it will be at that 7-minute mark. All right, without further ado, I would like to introduce Célia.
So hi everyone, my name is Célia Kupfer. I'm very happy to be here today to talk about concrete component reuse. So why talking about concrete reuse? We know that concrete is the most used construction material in the world. And cement, the binding agent of concrete alone, is responsible for 5 to 9% of global CO2 emissions and account for about 70% of concrete embodied carbon. The high demand in concrete also intensifies political and economic conflicts around sand extraction and stresses on water reserves. But still, despite the large demand in concrete, ever younger concrete buildings that are in a good state are regularly demolished and crushed into rubble, causing the loss of the energy, history, and technology embedded in them. Today, demolition rubble is used for road construction or at best recycled as aggregates in so-called recycled concrete mixes. However, those mixes have in average similar CO2 footprints to new concrete mixes because they require the same amount of fresh cement, plus they still require the same amount of sand and water. For this reason, other solutions for discarded concrete remains to be investigated. When a premature demolition is absolutely unavoidable, techniques exist to saw concrete structures into large pieces using, for example, circular saws. When sawing a structure, whole structural elements can be extracted from them, but what can be built from these urban mined elements? The idea of reusing concrete to build structures is not new in construction. In past research, we showed that more than 50 projects with structures completely or partially made of reused concrete pieces have been built in Europe and in the USA since the late 60s. Now a question for us, can we spot a common feature between the majority of these projects? Well, most of them reuse prefabricated components as their dismantling is eased by pre-existing clear connections. Besides prefabrication, cast-in-place concrete is also a widely used construction method. But cast-in-place structures are large monoliths without clear separations between parts. So when aiming to reuse them as components, design teams must decide on the shape of the concrete pieces they want to extract, and that's a playful challenge. Today, I will present 3 approaches for reusing cast-in-place concrete pieces. The first one, on the left, reuses small blocks under compression. The second one, in the middle, reuses long slab elements using both their compressive and tensile strengths. And on the right, the third approach reuses large 3D assemblies, preserving existing connections between vertical and horizontal elements. Starting with the reuse of blocks, we designed a 10-meter spanning arch footbridge built with 25 blocks of reused concrete. In 2021, it was installed as a public footbridge to cross a river in the Alps. The blocks were extracted at their final dimension from a building undergoing transformation. The blocks were drilled and installed on the timber centering, and joints were filled with mortar. Finally, the pre-stressing cables were pre-stressed. Here you see the full arch. A life cycle assessment analysis confirmed large CO2 savings compared to new concrete designs of about 2/3. Most of the remaining CO2 emissions are caused by the timber production from the centering and the block transportation. All the hypotheses we did are detailed in a paper listed in the bibliography. During my PhD, I explored the second approach that values discarded concrete slabs by reusing them again in bending in new floor systems. If the slabs are long enough, they span directly between the supports. If they are too short for the new project, they can be installed over primary girders. To move from theory to practice, we built a 30 square meter office floor mock-up with concrete elements salvaged from a demolition site in Geneva. We then built the floor mock-up, placing the 3-meter long slabs over 5-meter long second-hand steel girders. During the project, we conducted several material testing, and a load test also confirmed that the system behaved as well as needed. an LCA, and you will find the details also in the bibliography at the end, of the prototype confirmed our preliminary results, with upfront embodied carbon reduced by 83% compared to a conventional flat slab with new concrete. The third approach proposes to reuse large 3D assemblies. We studied this approach via the Rebuild Pavilion, an EPFM student initiative. The pavilion's load-bearing structure is mainly made with reused concrete assemblies, and the rest of the building is made with other reused materials and bio-based materials. The 3D assemblies were socket in a building built in the 1970s and located 4 kilometers away. Its structure was made of pre-stressed flat slabs on a grid of mushroom columns. The Rebuild Pavilion was a catalyst for 3 other projects which reused flat elements sewn also from this donor building. An engineering office, the Société Coopérative 2401, coordinated the operations. The extraction of the 3D assemblies was technically challenging as they were extracted from 2 stories simultaneously. The assemblies were installed in 1 day and contributed to an original local project. Since the assemblies were installed, students and volunteers are progressively building the remaining building layers. On the right, we see the roof tiles painted by kids from the school where the pavilion is installed. In conclusion, when a demolition is absolutely unavoidable, concrete reuse is a promising approach to preserve the history, technology, and carbon embedded in existing components. Still, reuse remains a palliative solution to premature demolitions, and their reduction remains absolutely a top priority. Finally, concrete reuse today still faces major synchronization and cultural transitional barriers that some actions might help reduce, such as the development of mandatory reclamation audits or the development of new design guidelines, as Norway just started last year with the publication of a first standard to reuse hollow core slabs. If you wish to learn more about our research, we published a summary of it in the last April issue of the Structural Engine. That's it for me. Thank you so much.
Thank you so much, Célia. Now, Zoe, if you could share your slides and take it away.
Perfect. Okay, thanks everybody.
Thank you.
So, hi everybody, I'm Zoe Rogers. I'm an Associate Sustainability Consultant within WSP. I work within our Sustainability and Climate Change team there, mostly on infrastructure projects, as my background is in civil engineering, but I also head up the UK side of the LCA and the EPD work that we do there, which is also largely within the infrastructure sector. So today I'll be covering a bit about PAS 2080, the 2023 version, giving a brief overview for those of you who might not have heard of that. So some of the basics, but also highlighting some of the key changes since the last version in 2016. So a bit about WSP and PAS 2080. So PAS 2080 is a standard that you can get accredited to, which is something that WSP have for the last 2 years, which has been great for us to be able to do that. It's also meant that we've been able to help other organisations, such as National Highways as well, achieve this level of accreditation. We also work right down to the project level for many clients, helping them sort of identify how they can become PAS 2080 aligned. So we've got extensive experience in this area within WSP, including one of my colleagues, Lewis Barlow, even sitting on the sort of latest draft panel for the latest version. So where did sort of PAS 2080 come from, and sort of why do we need it? So it originated after the infrastructure carbon review, which I'm sure sort of from the UK perspective, which I'm sure many of you are aware of. Many of you will be familiar as well with these figures that I'm currently sort of showing on the screen there around how the infrastructure industry in particular impacts the UK carbon footprint. And it's broken right down there into what the infrastructure industry can control, but also what we influence. And this control and influence theme is something that has very much been picked up on in the latest PAS 2080 audit. So you can see there that the infrastructure does have a large impact on emissions here in the UK, and I'm sure that is common globally. So in order for us to achieve that net zero transition, we really do need a standard that encourages better carbon management processes, and right down throughout the businesses right down to project levels. But what actually is PAS 2080? Well, it's a global standard that very much focuses on that carbon management process side. So it's the what of carbon management, looking at leadership, looking at governance and continuous improvement. It is not the how do you do the carbon assessments. So for example, we've already heard from Jane earlier on today about the RICS whole life carbon methods of calculating your carbon footprint there. That is very much the how, and PAS 20 sort of points you in the direction of how to do your carbon assessments, but really is the structure that comes in around that. So what has sort of been updated in PAS 2080 since the last version? So in this 2023 update, well, now the latest version, very key and very, very important for this group, is that it now includes the whole built environment. So previously, it was very much focused just on that sort of infrastructure sector, so around your highways, things like that. But now there's a specific mention in the title to buildings. So that makes it, very much built environment focused. It's taking much more of a systems thinking approach. So really trying to sort of go top down as well as bottom up, and taking that systems thinking approach towards net zero as a whole. That also links to my point on the left there around nature-based solutions and resilience. We can't just be talking about carbon on its own. We need to be aware of those other topics. And I think that has also been sort of referenced in earlier talks as well. There's some key themes that I'll get into in a bit more detail, which have sort of slightly tweaked, and the general sort of feel of PAS 2080 is slightly different. It's moved away from the sort of carbon calculation, as I mentioned, which feeds into that decision-making approach and whole life carbon sort of setup as well, which I'll get into in a bit more detail in a moment. So in terms of that systems thinking, well, it's the scope of PAS 2080 is something that has been slightly tweaked or sort of more clearly defined throughout this new document. So you can see there by this diagram that's from PAS 2080 that we really do include sort of the whole value chain and everybody within this system of infrastructure, of buildings and within the built environment. Because the things that we tend to work on are assets which make up networks, which make up the whole system. So we really do need to be including everybody within this process. So you can see, for example, the sort of bottom four, this is relevant for designers, it's relevant for constructors, the sort of material suppliers, everybody within this process. And again, as well, you can see by the arrows that are on this diagram, it's denoting the difference of what can we control. So who can control the asset level, who controls the network and who controls the system, but also everybody has an influence across all of those. So it's something to be mindful of. In terms of the key themes, these are now the sort of main areas that sort of come out of PAS 2080. So it's very much about leadership. So it's why it's sort of slightly removing away from it used to be very project specific. It's now looking at organizations as well. So how can a sort of organizational leadership take control in terms of procurement? So what are we putting in the procurement processes to make sure carbon management is happening throughout a whole project? What are we doing about collaboration and how can we foster that? Are we looking more closely at those risk-based approaches and taking a bit more risk in order to achieve better carbon reduction? Systems thinking, as I've already mentioned, and also looking much more closely at the tools and the data. And really key is that consistency. So obviously today is a lot about greenwashing, and that's sort of covered in this process a bit more now, in terms of this carbon management process and the governance that you see on the screen there. So that claims of conformity, which is sort of clause number 12. So each of these numbers identify clauses and have points behind them. Those claims of conformity really are to sort of make sure what we are saying is fair and true. The diagram on the top left is what this used to be in the old version. So they have tweaked it to include things like leadership and to really sort of show that iterative process in terms of a circle, and that it happens at every work stage in a project. And it's very much focused on integrating carbon decision making throughout the life cycle of a project and throughout the life cycle of a principle. So yeah, so this is a key change to the latest version is around governance. This is another big change for the diagram, for the latest standard, and this is the decision-making process that I mentioned at the beginning. So quite a lot on the screen, but what I mean in summary is at the top where it says build nothing, build less or build clever and build efficiently. Those are the old definitions that we use. There's now, it has been simplified to avoid, switch, and improve. And I think this works better, because when you talk about build nothing, you're thinking very much, the building on its own and things like that. But actually, this can now look into the products. So it can look into steel, it can look into concrete, and we can get right down to that product level to say, can we avoid this material, or do we need to switch and improve? So that is a big key change there. There's also a lot around the sort of whole life carbon assessment. So I think this is something that also Jane touched on, so I won't go into this diagram in too much detail, but just saying that it is referenced here within PAS 2080. And again, it's talking around that sort of network and systems and how we're making sure we are looking at the whole life of a project, right from need through to operation. But in a bit more detail, again, you can see this general theme that is occurring throughout PAS 2080 around this control and influence. So this is a really big change from 2016. Previously, PAS 2080 referenced the life cycle stages of A, B, C, D. Now they've left that to RICS, that's in the calculation process, and they've just simplified it down to before use, and after use. So that is a big change people need to be aware of in terms of the calculation process. And then lastly, just the benefits of PAS 2080 and how it can be relevant to sort of everybody. So you can see the theme here is around the big C's, but some key ones that I'll pick out is that consistency around data management that I mentioned, that credibility in making sure we can prove the calculations that we've done and making it robust, and collaboration is obviously very key. But continual improvement in what we do to make sure we're absolutely maximizing carbon reduction is obviously the key focus of it. So that's me.
Thank you, Zoe. Like to now introduce Mel.
Cool. So my name is Mel Chafart, and I am a research engineer at the Carbon Leadership Forum. And what I'm going to be talking to you about today is not work from the Carbon Leadership Forum, but it is what I am working on with SE 2050. Jay here talked today about some SE 2050 stuff, and I'm going to talk about what SE 2050 is, what the SE 2050 database is, and what we collected, what we found, and moving forward. And mostly what I'm going to be talking about is the data that we collected for the SE 2050 program. So what is SE 2050? SE 2050 is a signatory program whose mission is for structural engineers to understand, reduce, and ultimately eliminate embodied carbon in their projects. There is a program mechanics portion where people have embodied carbon action plans, and there's also a reporting portion where people report information such as data. Sorry, I have the 20-second timer on. Anyway, so this data we analyzed. Who is we? We is me, Dimi Fong, Jonathan Broyles, and Martin Torres, and we analyzed the data that people have submitted. This data has a bunch of really interesting characteristics. It is only substructure and superstructure. The objective is global warming potential, where that's the only objective that we're collecting. We're relying on people to supply global warming potential based on the tools, and we collected biogenic carbon, but it is not included in the analysis. So what we collected was a lot of structural information, and I think what's most important here is that these are really exciting design choices and criteria that we are looking for, that we're very proud of collecting because it is very rich information. On top of that, we're also collecting a lot of global warming potential data, total GWP, LCA tool used, as well as biogenic carbon and biogenic carbon GWP. We will then have this GWP intensity, which is total global warming potential divided by square footage. So what did we receive? We received many projects, over 500 and over 600 projects at the current time, but we will be analyzing around 520 for this report. We received office and education projects, multifamily residential, over 250 steel projects, 150 concrete projects, and over 75 wood projects. I'm going to have to talk about life cycle stages here for a bit. Life cycle stages are important because we needed to partition the data as it was not totally aligned. We needed to ensure that we're talking about upfront carbon, which is product level data, as well as embodied carbon, which includes end of life. So When we received 500 projects, what we really mean is that we had to kind of whittle this down. And so we cleaned these projects by making sure all projects in North America were there. We removed renovation projects at the moment. And then we had to partition this data, since combining projects that have end of life without end of life is not exactly a fair assessment. So we partitioned the data into upfront carbon right now and a to C data set, which includes end of life. Because structural engineers have the most impact for the materials that they procure, and because it was the largest data set that we had, we chose to use upfront carbon as the data set that we plot. So I'd like to talk a sec about box plots. We're going to be talking about box plots here, and so we have our mean is going to be the X in the box plot. The line that we have within the box is the median of the data. Anything outside of the two whiskers is going to be considered an outlier, but we decided to keep those information because it's really important for us to understand that this is still very raw and exciting data. This is a regression plot, and what we're going to be talking about is global warming potential, total global warming potential against gross floor area. And so what we see is the highest correlation here, and this is something that I'll talk about more in the key takeaways, but this is the highest correlation that we found within our data set. We also checked this against some other key features that we thought would be very important, such as mean roof height and stories above grade. But what we found was that there was no real correlation here. We found that this was very exciting, and I think it's something that, or maybe not exciting so much as interesting, in the idea that we need more data to understand this more in depth. We checked this in a bunch of different ways as well, not only by total GWP, but by GWP intensity, and also in log-log regressions, and we still found no clear correlation. So this is something that we think points to the idea that we are in need of some more data, but also that there may not be a clear correlation between something that we thought was very strongly held. On top of that, we looked at GWP intensity by building use type and some structural systems. Here, what I want to highlight the most is the amount of spread that there is in this data. What's really interesting here is that these spreads are very large, and it's hard for us to make some clear distinctions about global warming potential across building use type. This also occurs for a horizontal gravity system. These spreads make it very difficult for us to understand what is the most important, but the trends here are that concrete and steel are typically showing up as the more global warming potential intensive projects, with wood being slightly less. But again, these are early stages. What I want to highlight in this last portion from primary lateral system is why this is still early stages, because as you'll see, steel moment frames is currently the highest. But if you were to remove the last those two outliers at the very end, this would be a lot closer to concrete shear walls at around 298 kilograms per meter squared. So what we're seeing is that this is still very early. And that's one of the big key takeaways, is that the data is in its early stages and we can start to see trends, but the data quality is coarse. Still, gross floor area is the highest correlation with embodied carbon, which is very interesting and points to the idea of size of our projects is important, and concrete and steel are higher emitters than wood. And then finally, this database improvement has allowed us to make some updates to the database itself. We've been asking to report by life cycle stage, so we no longer have to do these partitioning of the data. And we also wanted to collect material quantities and are looking to have biogenic carbon, more guidance on biogenic carbon. And that is all I've got. So thank you very much.
Thank you, Mel. No mean feat doing it in the Petra Kuchar style of 20 seconds. So thank you very much for that. Now introducing Eva, who will be also following that same pattern as well.
So hi, I'm Eva MacNamara. I'm a director at Expedition Engineering and the Useful Simple Trust. I'm here to talk about our research on the embodied biodiversity impact of construction materials, which was co-funded by ourselves as the Useful Simple Trust and the ICE's R&D Enabling Fund. And it was released about the same time as the UK GBC's work on the same topic. So back in 2019, Expedition Engineering signed up to Structural Engineers Declare. Many of you will be from organisations that have done the same. And when we signed up, we declared a climate and biodiversity emergency. Most of us here today understand the precariousness of the situation associated with the climate crisis and carbon, but biodiversity has some catching up to do to be as well understood. And you don't just have to take it from me. Antonio Guterres, the UN Secretary General, gave a strong statement at the 2022 COP on biodiversity, and he pointed specifically to construction as an industry that needs to act and incorporate their impacts on nature into their business plans. So our response to this, and inspired by the design approach to our work on the Eden Project in Dundee, was to do a piece of research on the embodied biodiversity impacts of construction materials. We focused on the embodied biodiversity impacts because whilst awareness and action around biodiversity impacts on site has been increasing with biodiversity net gain, the industry hasn't really moved forward on the biodiversity impact off site from our design and construction. So what does embodied biodiversity impact look like? Here's the largest quarry in the world, not in the UK, but we know that the UK construction industry uses around 37.5 million cubic meters of concrete every year, and that global concrete consumption is set to increase in coming years. Concrete production requires quarrying of limestone and aggregates, if not recycled. We also know that the UK construction industry consumes around 803,000 tonnes of steel per year, and that steel production is an energy intensive and chemical intensive process. So steel production also requires mining for raw materials. And this image is of a tailings dam in Australia, which stores the byproducts of mining operations. And those dams are usually highly toxic and potentially radioactive. And timber, which is increasingly relied upon as a low carbon option, was historically grown in monocultures and still is in some supply chains where its procurement is not under sustainable certification schemes. So in all these materials and many more, we're impacting biodiversity in our hungry industry consumption, and we need to find ways to reduce that impact. But why is this important? Biodiversity ultimately underpins the resilience of the ecosystems we depend on. If you want to come at it from a financial perspective, the monetary value of goods and services provided by ecosystems is estimated to be around $33 trillion per year. But of course, value goes way beyond financial value. So biodiversity is in crisis. We have entered our 6th mass extinction event, and the first caused by human activity. Previous mass extinction events wiped out around 95% of all species, and it takes ecosystems millions of years to recover. And the UK has led the world in biodiversity destruction and is one of the most biodiversity depleted countries in the world. So the built environment is a significant contributor to this crisis, and the World Economic Forum identified it as one of 3 systems responsible for over 80% of global biodiversity loss. And if the infrastructure and the built environment impacted 29% of threatened and near threatened species. So as an industry, we're beginning to understand and positively influence biodiversity on site with biodiversity net gain, but biodiversity net gain doesn't cover every impact. All of the materials making up those assets, so concrete, steel, timber, earth, and so on, require raw materials to be extracted, manufactured, transported to site, and managed at end of life. So, analogous to carbon, the whole life cycle of these materials needs to be taken into account for biodiversity impact. And a key difference between carbon and biodiversity is that within reason, carbon emissions have the same global warming potential wherever they are released around the planet. But biodiversity impact is a degree more complex because of the local effect, both the magnitude of the hazard matters and to which local ecosystem it's applied to. But as with carbon, as practitioners in the built environment, we can influence the biodiversity impact of our projects through the decisions that we make about materials. So considering embodied biodiversity impacts is an essential part of becoming a nature and people positive profession. So a little bit about our research. Our research was very focused at drawing useful conclusions for the construction industry as early as possible to create a springboard for wider action. We structured it using the COM-B model for behavioural change, something Expedition use often in our innovation work. And the COM-B model considers capability, opportunity, and motivation to enable us to output practical actions. So importantly, we didn't want to reinvent the wheel with our work. So to understand how each material impacts biodiversity, we used the UN's 5 pressures on biodiversity. We didn't consider carbon impact as we felt this is already covered, and we didn't want to, we wanted to clearly understand biodiversity. So we considered the life cycle impacts on through land use change, direct exploitation of species, pollution, and invasive species, which you've seen on the previous slide. And for each material, concrete, steel, timber, earth, and asphalt, we took the following steps. We defined material assumptions, mapped the life cycle, found evidence through those 4 UN key pressure lenses, and rated the severity of the impact. And for that, we used a biodiversity impact expert to help us. We then gathered the results into a diagram which describes the impact across the life cycle and summarised the assumptions of our research and key findings for each material. This should look familiar as it follows the same structure as a typical LCA in line with industry guidance. This example is for concrete, which has a relatively short and more local supply chain than, say, steel. In the report, we have set out steps for the industry based on the COM-B model I mentioned earlier. Being able to quantify embodied biodiversity impacts feels like a long way off. We know it took decades for embodied carbon to move from research into industry practice. So in the meantime, we can set out some high-level industry actions that we can get on with now. They're focused around reducing extraction of raw materials through minimizing the amount of material needed, maximizing circular economy principles through reuse, or else ensuring that extraction is done responsibly, which requires an in-depth understanding of our supply chains. In reflecting on our research, we saw that it aligns strongly with the actions for carbon and with the IStructE's permission produced this adaptation of their hierarchy of net zero design. So please take a look at our report and as well as that, the excellent further reading, which can be found on the UK GBC's Embodied Ecological Impacts website. You'll also find useful resources in the Donut for Urban Economics and Natural England's Biodiversity Metrics to understand more about the construction industry's impact on biodiversity. Thank you.
Thank you very much, Eva. Now introducing Clotilde.
So good afternoon, everyone. I'm Clotilde Robin. I'm a director at Expedition Engineering, so working with Eva that just presented. And today I'm going to represent the Net Zero Bridges group and give you some insight about what we've been doing and some of the challenges. So our objective is to accelerate progress towards net zero carbon bridges by sharing knowledge and ideas and shaping best practice. We now have 37 members organizations. We represent most of the bridge design and engineering firms in the UK and Ireland. We remain entirely independent and unfunded. We were set up to focus on bridges, recognizing that they are carbon intensive, but also critical to the transport network. And that's also what we are good at as bridge designers or bridge engineers. And when we set up the group, we tried to refine the scope to be more efficient and focus only on carbon, with an emphasis on the role of designer, because many of us were designers when the group was created. In practice, we are a knowledge-sharing group with bi-monthly sessions with all members, doing presentations, discussions, sometimes debates. We also invite external persons, such as clients, to share their point of view and reflect on their challenges. We have a website and a linking account to share news, case studies, and also to reach a wider audience. We actively participate to conferences. So, for example, recently at the IAPSE Symposium in Manchester, more than 10 members of the group represented the Net Zero Bridges group and talked about some of the themes we're working on. We are also present in a client's organization. The BOF is the Bridge Owners Forum, to engage with clients and talk about, for example, funding challenges, maintenance, repairing, and replacing assets. So this slide is just to show a few publications on various topics that we are working on, all related to bridges. We have subgroups leading the charge on different topics, so to make sure that we are remaining active. So I will introduce now two topics that we are currently working on. So the first one is about data gathering, so carbon data gathering and benchmarking. We strongly believe on data sharing and transparency. So we also need this data to make informed decisions. So therefore, we are calling all members of the group and everybody we know working in the bridges industry to share the embodied carbon data of their past projects with some details about the project that we can then anonymize. But we want this data to be able to reflect on which typology or which span are more efficient. However, we're also conscious about the impact of in-use data, which is much more difficult to measure. So it's crucial to understand where it is. And so, for example, when doing maintenance or repair works on a bridge, we know and we start to measure the impact of deviation, traffic congestion, and plant use during the repair works. And minimizing time, maintenance times becomes quite critical and an opportunity to reduce the carbon impact. Another system view is to consider the benefits around building a new bridge, which is going to, of course, come with some embodied carbon, but maybe bring some benefits into the wider transport system and to relieve some of the cars and driving effect and replacing by cycling and walking. This is not something we typically measure on bridges, but we want to get to that point. This system thinking approach is encouraged by PASS 2080, and Zoe talked about that. I'm leading the subgroup focusing on publishing a guidance for bridges. We've produced this diagram explaining the carbon reduction hierarchy put forward by PASS 2080 and explaining how you can apply that for bridges. So I'll pause a little bit on this slide so you can have time to read some of the text and some of the key questions and requirements one should consider when working on a bridge project. The inner circle is about bridge specifics indication, whereas the outer circle is calling for holistic thinking. So if we look at the first segment, avoid, we can see if we look at the bridge, one of the questions is a bridge needed at all? Then can we widen an existing bridge? But also question about the wider system. Can this transport outcome be achieved through other lower carbon means? We focus a lot on avoid because we are conscious that this is the area with the greater impact on the carbon reduction. So what PASS 2080 means by avoid is align the outcomes of the projects and or program of work with the net zero transition at the system level and evaluate the basic need at the asset and or network level. So it's a bit more complex than build nothing, as Zoe explained. And we're trying to translate that into action for people working on bridges. So three main actions, three focus areas are repair. We now have a fully developed transport network with lots of footbridges that are 50 or 60 years old and they need maintenance, they need the repair works. Repurpose, it's about, for example, all railway heritage viaducts that are not fit for purpose anymore, but can be used for cycling and pedestrian and encourage active travel. And reuse is about encouraging a circular economy. And I think that was the first, the example is the first presentation about how you can reuse some existing concrete blocks into a new project. So I'd like to conclude now on what we think it's time for as a group. We are really calling for action. Of course, it's still important to raise awareness and inform, but time is ticking. So many of us, we know about the challenges. And what we want is to provide useful support to find solutions and encourage good practice. Thank you.
Thank you very much, Clotilde. Really interesting to hear about the Net Zero Bridges group. And then last but certainly not least, we got Orlando with an update to the IStructE carbon calculation guidance and tool. So take it away, Orlando.
Thanks, Tasha. It's great to be joining you all here for the last session of the day. So I'm going to give you a brief overview on the updates for the third edition of the How to Calculate Embodied Carbon Guide. So what is the How to Calculate Embodied Carbon Guide? It's a common method and set of principles for embodied carbon calculation for structural engineers. This allows us to do meaningful comparisons between designs, improve understanding of carbon of structures, and focus our design efforts to minimize carbon. That will ultimately help us to reach net zero emissions. The guide applies to structures across bridges, buildings, and infrastructure, and it was co-authored by myself, John Orr, and Will Arnold. So why are we updating this now? Well, if you didn't get it from Jane's presentation earlier, the RICS Professional Standard second edition is effective from the 1st of July. So we're trying to update our guidance to match that. There's loads of new guidance in the industry. It's being produced all the time. It's fantastic. We wanted to incorporate that. There are updated carbon factors. It's 2 years since we've last issued the guide. So we're more experienced and more knowledgeable, and that should be reflected in the guidance. So a brief overview of the updates. There are updates to life cycle modules, concrete, steel and timber guidance, carbon factors, building elements, scope guidance, default material quantity allowances, bridges guidance, following on from the net zero carbon bridges talk just then, and some other notable references to the RICS professional standard. And I should say that a lot is based on the RICS professional standard, but there's more than this list. So this diagram is the life cycle modules diagram. The ones highlighted in red are the ones that have something changed about them. The one in pink on the left, A0, is a new module in the guide, which is kind of a for some projects may be negligible, but for other projects, especially infrastructure projects, might be quite significant. So these life cycle modules have additional. This slide just really highlights which ones have now been broken down into multiple sort of sub-modules. So A5 has 4 subcategorizations, B1 has 2, B4 has 2 subcategorizations, and kind of unique to our guide is a suggestion of how you could break down C3 and C4 into 2 subcategorizations, talk about emissions and transfers separately, which I'll get onto in a bit. So firstly, A1 to A3 carbon factors, we're updating the carbon factors for steel sections, rebar, timber, intumescent paint, PT strands, and we're also adding some carbon factors, especially around low carbon materials, so bamboo, rammed earth, adding some concrete grades, stainless steel, reclaimed brick, unfired clay brick, hempcrete, asphalt, bitumen, and also fiber composites, so expanding that table a bit too. Changes to other carbon factors. So there are some changes to the A4 carbon factors using the latest government greenhouse gas reporting factors. It accounts for the return leg, but we always recommend kind of the most accurate A4 calculation, calculate it yourself based on kind of a first principles calculation. A5.1 is a new module, has a similar impact to A5.2. And A5.2 is now a carbon factor based on kilograms of CO2. So that says kilograms, it should say meters squared of GIA rather than kilograms of CO2 per 100,000 pounds. A5.3, waste rates are updated and align with RICS. C3 and C4 also updated to align with RICS. It used to be just one flat rate that we applied to all materials. Now there are 4 different material categories, each with a different carbon factor. And the timber end of life scenarios factors and have been updated too. And I'll just move myself out of the way. And module D, we're updating the carbon factors there to align with the A1 to A3 carbon factors. We've updated slightly the concrete guidance to really limit and acknowledge the limit on GGBS availability. And we also kind of highlight ways to reduce reinforced concrete structures embodied carbon. So reduce demand for material, reuse concrete, design for technical performance, optimize the reinforced concrete section rather than just trying to use the least amount of concrete possible. Early collaboration with the contractor helps with getting the specification through. Reduce use of Portland cement to reduce the embodied carbon of the concrete itself, but do not focus on specification of high portions of GGBS. We also have some guidance on steel, which again acknowledges the limit on scrap steel availability and kind of highlights the ways to reduce steel structures embodied carbon of, first of all, minimizing total weight of steel, reusing steel, specify from producers who are decarbonizing their manufacturing, but do not focus on specification of scrap-based EAF steel. Timber guidance, we've acknowledged that there are dynamic LCA methods to aid options comparisons, and this really helps when we compare timber and steel and concrete. We have this biogenic carbon value for timber that we don't really know how to, it's not very clear how to kind of incorporate that into the general comparison. If you want to have a bit of a hand with doing that, then dynamic LCA methods that the RICS guides describes can be used. Timber end of life emissions, we've suggested breaking that out into transfers and emissions. As you can see on this graph on the right, this is these are carbon factors for CLT, and you can see in the blue bar on the right hand side, that's kind of the difference in transfers and emissions at end of life. So emissions are actually real emissions of greenhouse gases, and transfers is just really is counted as an emission in typical life cycle assessment practices. but really nothing is emitted. It's just it's an accounting method of accounting for a transfer of the biogenic carbon stored within that product to the subsequent product life cycle. And also we go through ways to reduce timber structure embodied carbon. So again, reduce demand for material, reuse timber, source from sustainably managed forests, and keep timber in use as long as possible to keep that biogenic carbon in there and not in the atmosphere. Just to kind of emphasize the minimum scope that we're recommending for building elements. So you should be calculating any elements in your scope of works. Also, and this is kind of like the maximum of these three things, the primary structural elements within your structure, but also the materials that enable your structure to meet its performance requirements. So fire protection, vibration, and blinding, vibration, dampening and blinding, for example. We also, this is something new in the guide, we provide some default material quantity allowances to help with those additional materials. So for reinforced concrete, laps, blinding, temporary formwork, steel, we provide some rates for connections, sprayed concrete and intumescent paint, and timber for connections, fire protection and acoustic insulation. Bridges guidance used to be in the second edition, it was a kind of an appendix C, so supplementary information that was added on at the end. What we've done in the third edition is really incorporated that into every section with updates from the Net Zero Carbon Bridges group. Thanks to Cameron from Cowie, and yeah, so now that's kind of more integrated. And even though it's kind of bridges specific, there are principles in there that apply to other types of infrastructure structures. Other notable references to the RICS professional standard, second edition, is we kind of point towards it in relation to the use of uncertainty factors, material decarbonisation allowance, which really affects, as Jane explained earlier, stages B and C of the life cycle, dynamic LCA methods, which I've already mentioned, and also kind of a bit of guidance on normalising total absolute carbon emissions for assets with partial refurbishment, new extension, and untouched areas. So how and when can you access this? It's going to be published at some point in August 2024. The draft went to the publishers this morning, so it's really hot off the press. Members will be able to access it for free, as they always have been able to. You can pre-order for a 10% discount for non-members, and the changes will be reflected in the structural carbon tool, thanks to the great team at Elliott Wood who have been producing that. And also thank you so much to the reviewers. And that concludes that section. Thank you.
Fabulous. Thank you so much. I'd like everyone to turn on their cameras, please, because we have a couple of questions. We've got 9 minutes for questions, so speedy replies will be greatly appreciated. I have a question for Célia about the structural capacity of used concrete elements. How are they estimated so that they can be reused? Are there any guidelines available for this? That's a question from the audience.
Do you hear me?
Yes.
Cool. So for guidelines, at the moment, the only standard that I'm aware of has been published by Norway. So Norway, a year or 2 years ago, published a standard for reusing hollow core slabs. It's a very detailed one, and I think it's a very exemplary work. And then at the moment in Switzerland, we use codes for existing concrete structures and new structures. That's how engineers work at the moment to design reuse concrete structures. And to know the capacities of the elements, we use destructive and non-destructive techniques. I mean, the ones you would also use for existing structures. So, and we also include carbonation depth tests and tests on both the steel reinforcement and the concrete. I mean, the usual techniques on site and in labs.
Well, thank you. I think we'll be downloading lots of Norway's standards from today. Thanks for that. Zoe, so with PAS 2080, I know I've heard about it for a couple of years. How are you finding uptake of that particular carbon management standard? And is there maybe like one thing that we can take away as an audience to get it more implemented on our projects?
Yes, yeah, uptake is been really good actually. So obviously going for the full accreditation process is quite a big piece of work, but there's lots that projects and organizations can do to align to the principles, which I think are very clearly set out in the standard, which does make it easier for engineers to follow, designers to follow, business leaders to follow. So I do think that does help. So in terms of one thing to take away, I would say it's about everybody taking ownership of the carbon management process. There will be a bit that is very relevant to your job, but everything is relevant to your role really in helping reduce carbon.
Cool. Thank you very much. Moving on to Mel, I really enjoyed seeing like the rigor that you applied for calculating the benchmarking. Has this been applied, or have other organizations or countries approached you to try and get this benchmarking process or method undertaken for their sort of stock of buildings yet?
Yeah, so I think the short answer is not yet. I think the longer answer is I think that I would feel uncomfortable saying that these are fully benchmarks. I think that these are like we're just a little too early to be able to say that. I think the box plots that I showed, like if we were to dig in a little more and talk about like what you can statistically like take from that, and like in terms of standard deviations, we would, and assuming this is maybe a normal or not normal distribution, the ranges are really wide. So it would be, I could confidently tell you that 75% of office projects are between 0 and 600 kilograms of CO2 per meter squared. And that is a huge range.
Yep.
And that is like not a lot to take away from. And that's what our data is showing right now. So I think that what we've started saying and what we feel comfortable with is that the 80th percentile of projects, and for your upfront carbon, so life cycle stages A1 to A5, is around 350 kilograms of CO2 per meter squared is what we're seeing. And so it's not a hard benchmark. I hope that this does not become like taken, because like again, like the data is still early. But when you see something above 350, we've started to say, hey, maybe this is something you want to reassess. This is like what we're starting, like a soft understanding of this is what is a good or not good number or something like that. Yeah, so that's I think where we've coalesced to right now, and I think we're not saying benchmarks for a good reason. I think we're just not there yet.
Thank you for the clarity. Now, moving on to Eva. I have two questions for you, but I will just ask one. What can I do specifically on one of my projects to support moving forward industry understanding on embodied biodiversity impacts?
Yeah, thanks. That's a helpful question. The UK GBC did their work at the same time as us, and they basically put a call out for more information. And I think if you look at what we need to do to reduce our impacts on biodiversity, it follows broadly the carbon reduction hierarchy. But what we're well behind on as an industry is when we started looking at carbon in more earnest, let's say 10 years ago, and obviously accelerating upticks, then the ICE carbon database existed, and there's nothing equivalent for biodiversity that really exists that's kind of agreed across the industry. So I'd say, can you follow the supply chain on just one of the materials on your project that you're working on? If we try and look at everything all at once, that's going to get quite complicated. So just follow one, go and visit the factories, go and visit the quarries, go as far along the supply chain as you possibly can. And I think as engineers, as we start to see, feel, taste, understand, what does a forested, sustainable forestry look like? What does a quarry look like? What does waste look like? And all of that, those sorts of things, then you start to sort of design, I think, a bit more intuitively, and we will get more data to feed in. So yeah, follow the trail on one project.
Thank you. Clotilde, Do we think knowledge, a question for you, do we think knowledge sharing is sufficient, and what are the other actions that the Net Zero Bridges group can support?
So I think knowledge sharing is a first step that we shouldn't underestimate. You know, it seems very obvious to do that, but it's not that common at an industry level to get people from different private companies, you know, working together, sharing lessons learned in an open, safe place. And the Net Zero Bridges group has successfully managed to create that. But another thing is that there is no magic solution. So it's not as if we could support one action and the problem will be solved, but things are moving quickly. So being sure that everybody is aware about what is on the market, what is being under research, what has been tried, I think is important. And that's all about knowledge sharing. But in terms of other actions, we are doing other things. So producing guidance, I think it was presented, you know, like a method to adapt the calculation of carbon to bridges, producing a rating that will be dedicated to bridges. So all it's beyond information. It's really defining some methods and approaches to encourage people to follow. We would love also to now move into supporting innovations, maybe testing, doing some partnership with universities, but we are an unfunded group. And that's where I think we are finding some limits. It's great because we are independent, because, you know, it's we don't have to follow an agenda, you know, that is different from what we think is important. But then there are some limits. So we are reflecting at the moment how we can join force with other people working on the same topic and having more pragmatic action.
Fabulous. Thank you, Clotilde. And then Orlando, a question for you. What are the changes people should pay particular attention to, and which ones might have, you know, the biggest impact on our calculations with the new?
I think the changes to the carbon factors, especially the A1 to A3 carbon factors, probably have the biggest impact, seeing as that's where the majority of our embodied carbon of our structures lies. So yeah, pay attention to those, but also just kind of the general changes to the other ones as well, just so you're kind of knowledgeable and aware of those changes, even if it's not affecting your project's embodied carbon. It might do in your next one.
Right. Thank you very much, everyone from session 3.